Very good morning, all of you. Today, I'm going to discuss another important reaction, metal hydride, the reduction of carbonyl compounds by sodium borohydride and lithium aluminium hydride. So this is a topic of interest today. So we'll see what happens when carbonyl compounds are subjected for reduction in the presence of sodium borohydride and lithium aluminium hydride. Okay. So usually the carbonyl compounds includes your aldehydes and ketones. Okay. These are called generally as carbonyl compounds. Okay. Now, for example, when aldehydes are subjected for reduction in the presence of sodium borohydride or lithium aluminium hydride, you are going to get a primary alcohol. Okay. For example, if you see the reaction, so you know the general formula for aldehyde is RCHO. Okay. Aldehyde, when it is subjected for reduction in the presence of sodium borohydride and lithium aluminium hydride, okay, you are going to get a primary alcohol. So this is a primary alcohol. Okay, so the difference between these two reagents, sodium borohydride is a mild reducing agent, whereas lithium aluminium hydride is very strong reducing agent. Okay, so when you are using lithium aluminium hydride, utmost care has to be taken because it can react with other acidic protons like carboxylic acids, amines, etc. in the structure. So those acidic protons can also be reduced. So take care when you are using lithium aluminium hydride as a reducing agent. Okay, whereas sodium borohydride is a mild reducing agent and it can be used very selectively to reduce aldehydes, ketones, acid chlorides without affecting other reducing groups like esters, epoxides, lactones, etc. So this is a main differentiating factor between lithium aluminium hydride and sodium borohydride. Okay, so already first we discussed about aldehydes. So when aldehydes are subjected for metal hydride reduction in the presence of sodium borohydride or lithium aluminium hydride, you are going to get primary alcohols. In the same way, if you take ketones, this is a general formula for a ketone, RCOR-. This is ketone. When it is subjected for reduction in the presence of sodium borohydride or lithium aluminium hydride, okay, you are going to get secondary alcohols. So this is your secondary alcohols. So this is a basic difference between the reduction process with aldehyde and ketone. Aldehydes will give you primary alcohols. Ketones will give you secondary alcohols. Okay, now we'll see the reaction mechanism for the conversion of a ketone into a secondary alcohol. Then we can see how aldehydes can be converted into primary alcohols. Okay. And the mechanism is also very simple. You can understand very easily in 2 steps. Now, reaction mechanism to convert ketones into secondary alcohols. So please pay attention so you can understand. So I'm going to explain this mechanism in 2 steps. Step number 1, nucleophilic attack by hydride anion. Okay. Now I'll write the basic structure of ketone here. R C double bond O R dash. This is ketone. Thus, I'm going to react with sodium borohydride, which is a mild reducing agent. So to understand the mechanism, I'm writing the structure of sodium borohydride in this way, Na plus BH4. Okay. Now, initially what happens is you compare the electronegativity between carbon and oxygen. As oxygen is more electronegative, the pi bond will migrate towards oxygen. Okay. Therefore, this carbon will become electron deficient. Okay. So you compare the electronegativity between boron and hydrogen. Please remember, boron electronegativity value is 2 and hydrogen electronegativity value is 2.24. So when you compare the electronegativity between these 2 atoms, boron is having least electronegativity. Okay, so if I break the bond between boron and hydrogen, the electrons will migrate to hydrogen. Therefore, hydrogen will get a negative charge. Okay, so this negatively charged hydrogen is usually called as hydride anion. So this hydride anion will be transferred to the carbon atom, which is having positive charge. Okay, therefore, this carbon can form a bond with this hydride anion. Okay, so you can write this structure R C single bond, because one pi bond you shifted towards oxygen, you will get only single bond oxygen with 3 lone pair of electrons, and this is R dash. And whenever this H minus migrates to carbon, this carbon can form a new sigma bond with hydrogen atom plus BH3. So if one hydrogen is transferred to carbon, you will be left over with only boron followed by 3 hydrogen atoms. Okay, so this is called as sodium alkoxide. Where from this sodium is coming again here? Why? Because since oxygen is having, so here you are having oxygen, okay, and to this alkoxide, the sodium will be joining here, which is called as sodium alkoxide. So this is the first step. So nucleophilic attack by hydride anion. So initially the ketone functionality. So this is your ketone, right? So the pi bond will migrate towards oxygen. Therefore, carbon gets electron deficiency. And to stabilize this carbon or to nullify the carbon atom with positive charge, we are using the sodium borohydride. So when you compare the electronegativities between boron and hydrogen, boron will have least electronegativity. So the electrons will migrate towards hydrogen to get a negative charge. So this negatively charged hydrogen, you can call it as hydride anion, where it will migrate towards the positively charged carbon. Therefore, this carbon can form a new sigma bond with hydrogen atom. Okay, so along with that, this BH3 will be liberated as a byproduct, and the so-called product you are going to get is a sodium alkoxide. Okay, now if you go for the second step, so second step is nothing but the protonation of alkoxide ion. So I'll write the structure of alkoxide here: carbon with oxygen, 3 lone pair of electrons, followed by R, H, RH. Okay, so this is sodium alkoxide, what you got in step number 1. So this sodium alkoxide, I'm going to react with a solvent called as methanol. So to understand the mechanism, I'm going to write the formula for methanol in this way: CH3O single bond H. Okay, now if you compare the electronegativity between oxygen and hydrogen, oxygen is more electronegative. So when you break the bond, the electrons will migrate towards oxygen atom. Okay, therefore this hydrogen will become positive charge. As oxygen is having 3 lone pair of electrons, so 1 lone pair it will donate for hydrogen atom. Therefore, this hydrogen atom will migrate towards oxygen to form OH like this. So this is methanol. Okay. So you're going to get C single bond OH. Okay, R, CH, R dash. This is your secondary alcohol. Okay, so here oxygen is having 3 lone pair of electrons. Why? Because when you break the bond, the electrons will migrate towards oxygen. So oxygen will get 3 lone pair of electrons. So this extra lone pair of electron, I will donate for sodium. Therefore, you will get a byproduct called as CH3O Na. This is called as sodium methoxide as a byproduct. So this is how a ketone can be converted into a secondary alcohol in the presence of sodium borohydride. Okay. Similarly, we will take another important mechanism to convert aldehydes into a primary alcohol in the presence of a strong reducing agent, that is lithium aluminum hydride. Okay, so this mechanism shows you how a ketone can be converted into a secondary alcohol. Next, we'll see the reaction mechanism to convert aldehydes into primary alcohols. Okay, so as usual, step number 1, I can explain it in 2 steps. Okay, step number 1 is nucleophilic attack by hydride anion. Okay, now you can write the structure for aldehyde. R, C double bond O, H. This is aldehyde. Okay, so this aldehyde, I'm going to react with a strong reducing agent, lithium aluminium hydride. Okay, so this is a structure for lithium aluminium hydride. So initially what happens, the pi bond which is present in this carbonyl group will be shifted towards oxygen as it is having more electronegativity. Immediately this carbon will become electron deficient. So in the next step, what happens? You break the bond between aluminum and hydrogen. So aluminum will have little bit less electronegativity. So when I break the bond between aluminum and hydrogen atom, the electrons will migrate towards hydrogen. Therefore, this hydrogen will get negative charge. Okay, so this negatively charged hydrogen, you can call it as hydride anion. Okay, so this hydride anion will migrate towards the positively charged carbon. Okay, so now you can write the structure R, single bond oxygen with 3 lone pair of electrons. Okay, so this is plus lithium alkoxide. Okay, you are going to get one intermediate compound called as lithium alkoxide. Okay, so what is the second step now? In second step, it is nothing but protonation of lithium alkoxide anion. So step 2 is protonation of alkoxide ion. So once again, I'm going to draw the structure of lithium alkoxide. Okay, thus I'm going to react with methanol, or you can use water also, any solvent. Okay, so this is water. So if you compare the electronegativity between oxygen and hydrogen, oxygen is having more electronegativity. So the electrons will be migrated towards oxygen, making hydrogen electron deficient. So as oxygen is having one extra lone pair of electron, it will donate for this hydrogen atom to form OH. So you will get OH, R plus lithium alcohol as byproduct. So this is your primary alcohol. This is how the aldehydes can be converted into primary alcohols in the presence of lithium aluminium hydride. In the same way, ketones can be converted into secondary alcohols in the presence of sodium borohydride or lithium aluminium hydride. Okay, so this is how the metal hydride reduction of carbonyl compounds takes place in the presence of a mild and strong reducing agents. Okay, thank you very much.